Dear students, today I am going to explain you about vector spaces. Before explaining about vector spaces, let me recall some basic definitions. In 1844, Harman Grassmann gave the introduction of vector space. In 1888, Peano gave the definition of vector space and linear maps. You know what is a vector? Vector has both magnitude and direction. It is a physical quantity which has both magnitude and direction. But in mathematics, vectors denoted with line segments. Suppose here it is P x1 comma x2 is any point. OP bar is equal to R bar denotes the line segment. We represent vector as a line segment in mathematics. Scalars are often real numbers. It may be complex numbers also. Usually, the elements in the field F, we denote it as scalars. And you know the definition of the field. A field is a non-empty set with two binary operations, plus and dot. It is said to be a field. F plus is a abelian group. And with respect to multiplication, it is closed. It is associative. Ident element 1 belongs to F. And every non-zero element has multiplicative inverse. And AB is equal to BA for all A comma B belongs to F. And if it satisfies distributive laws, we call it as a field. These are the field properties. So you already know in the degree second year. Once again, I'm recollecting the definition of the field. Next, one more definition we need is internal composition. Suppose V is a non-empty set and F is a non-empty set. F is a mapping from V cross V to V. Then we call this mapping as internal composition. A mapping F from V cross F to V, we call it as external composition. So this is the meaning of internal composition and external composition. In the vector space, we denote internal composition as vector addition. Suppose V is a non-empty set. You take two vectors. Suppose U comma V belongs to capital V. Then U plus V belongs to again V. So V cross V to V. You take any two elements in V. Again, the mapping should be an element in V. So here U plus V is again belongs to V. So addition of two vectors is again a vector. And you take a scalar and to take a vector, scalar into vector, AU, it should be again belongs to V. That is called scalar multiplication. So the internal composition in vector space, we call it as vector addition, and external composition, we call it as scalar multiplication. So usually in the external composition, we take two different sets. Here V is one set and F is another set. In internal composition, we take V. So the elements in V should again map it to the elements in V. Okay, remember that. Next, a vector space. So vector space, we usually denote the symbol with V. So V is a non-empty set defined over the field F. And the compositions here are, one is vector addition and other one is scalar multiplication. So a non-empty set V, together these two operations, is said to be a vector space if it satisfies the following properties. What is the first property? V plus should be abelian group. So you know with respect to addition, it is an abelian group means it has to satisfy closure property, associative property, identity property, inverse property with respect to addition, and commutative property. So with respect to addition, you have to satisfy these five properties. See the first one, the sum of U bar plus V bar, U bar plus V bar. Addition of two vectors is again a vector. So we call it as the elements in V, we call it as vectors. The elements in the field, we call it as scalars. So addition of two vector is a vector. And it is a commutative property. U bar plus V bar is equal to V bar plus U bar. And this is associative property. U bar plus V bar plus W bar is equal to U bar plus V bar plus W bar. There is a zero vector 0 bar in V such that U bar plus G bar is equal to U bar for all U bar belongs to V. Next, for each U bar in V, there is a vector minus U bar in V such that U bar plus minus U bar is equal to 0 bar. And the scalar multiplication is closed. That means you take a vector, you take a scalar, and CU bar should belongs to V. So this is called scalar multiplication is closed. And other properties, C into U bar plus V bar is equal to C U bar plus C V bar. C plus D into U bar is equal to C U bar plus D U bar. C into D U bar is equal to C D into U bar. 1 into U bar is equal to U bar. If any non-empty set satisfies all these 10 properties, we call it as a vector space. So to show that any set is a vector space, the set has to satisfy all these 5 properties. So V plus dot is said to be a vector space. V plus is an abelian group. Under scalar multiplication, it is closed and it has to satisfy these 4 properties. Then we can say that V is a vector space. Okay, next I'll give some example. The set V together with these definitions of vector addition and scalar multiplication satisfying the above 10 axioms is called a vector space V, or V is a vector space. Some examples. For example, I'm explaining you the examples of vector space. For example, you all know that set of all real numbers is a field. I'm taking V as Q. I'm asking you, is Q of R is a vector space? This is my question. You know that set of all rational numbers is an abelian group under addition. So no problem. Q plus is a abelian group. Number 1. Number 2, take an element in rational number. Some U belongs to Q and A belongs to R. My question is, AU belongs to Q or not? For example, I will take some half in Q, root 3 in R. My question is root 3 by 2 belongs to Q? No, root 3 is a rational number. Root 3 by 2 does not belongs to Q. That means scalar multiplication is not closed. Scalar multiplication is not closed. Therefore, it is not a vector space. Same example, if I take R of Q, you know that R plus is a abelian group. An element in R, an element in U, the product again belongs to R. And all the remaining 4 properties, that is C into U plus V is equal to CU plus CV. C plus D into U is equal to CU plus DU. C into DU is equal to CD into U. 1 into U is equal to U. All these properties are true in this example, R of Q. So you take any product of real number into rational number, you will get a real number. In the number system, all these properties are true. Therefore, R of Q is a vector space. But Q of R is not a vector space because the product of rational into real is again real, not rational number. So scalar multiplication is not closed. So it is not a vector space. Take one more example, R of C. This is a field. You know that real numbers and complex numbers, they are fields. So R plus is abelian group. Very good. You know that. And the product of real into complex. The product of a real number into complex number is again a complex number, not real. For example, you take 3 belongs to R. And you take one complex number, 1 plus I belongs to C. 3 into 1 plus I, that is 3 plus 3I. They belongs to C, but they does not belongs to R. Therefore, the product of a real into complex, they belongs to complex, not real. Therefore, scalar multiplication is not closed. Scalar multiplication is not closed. Is not closed. Therefore, R of C is not a vector space. Same example, you take C of R. C plus C be abelian group. An element in C, an element in R, they again belongs to C. Or all the remaining properties are satisfied in C. Therefore, C of R is a vector space. So to check whether any set is a vector space or not, what you have to do? You have to check all the 10 properties. That is, V plus is abelian group. Scalar multiplication is closed in V. And remaining these properties. C into U plus V is equal to CU plus CV. C plus D into U is equal to CU plus DU. C into DU is equal to CD into U. 1 into U is equal to U. All these 10 properties are satisfied. We can say that it is a vector space. So for any problem, you have to do this. If one property is not satisfied, then it is not a vector space. So one more example. Show that R cube of R is a vector space. This is one more question. Now we will check it is a vector space or not. The first thing is, what is R cube? R cube means ordered triads x comma y comma x1, x2, x3. Each xi is a real number. Now my question is whether it is forms a vector space or not. So for that, what we have to do? We have to prove that it is an abelian group under addition. So let us take a vector u is x1, x2, x3. Let us take one more vector v, y1, y2, y3. Let us take one more vector w, z1, z2, z3. Now first question, u plus v. How will you define addition in the triads? This is x1 plus y1, x2 plus y2, x3 plus y3. So each xi is a real number, yi is a real number, xi plus yi is a real number, x1 plus y1 is a real number, x2 plus y2 is a real number. So three real numbers, so they belongs to R cube. So u plus v belongs to R cube. So addition is closed. Now my question is u plus v plus w. So what is u plus v plus w? So u plus v plus w is equal to x1 plus y1 plus z1, comma, x2 plus y2 plus z2, comma, x3 plus y3 plus z3. So this is the addition of the vectors. Okay. So this can be written as, because they are each one is a real number. Each one is a real number. Xi plus yi plus zi can be written as xi plus yi plus zi. This is true in the number system. So we can written as x1 plus y1 plus z1. This can be written as x2 plus y2 plus z2. And this can be written as x3 plus y3 plus z3. So this is same as x1 plus y1, comma, x2 plus y2, comma, x3 plus y3 plus z1, comma, z2, comma, z3. So this is nothing but u plus v plus w. So u plus v plus w is equal to same as u plus v plus w. Associative property is true. Next, identity property. U bar is equal to x1, x2, x3. And 0 bar is equal to 0, 0, 0. U bar plus 0 bar is equal to x1 plus 0, y1 plus 0, x2 plus 0, x3 plus 0. That is nothing but x1, x2, x3. That is equal to u bar. Next, u bar plus minus u bar. That is x1, minus u bar is nothing but minus x1, minus x2, minus x3. So u bar plus minus u bar is x1 minus x1, x2 minus x2, x3 minus x3. That is 0, 0, 0. That is nothing but 0 bar. So u bar plus minus u bar is equal to 0 bar. Inverse property is satisfied. Next, u plus v. That is equal to x1 plus x2. Next, x1 plus x2, y1 plus y2, and z1 plus z. Sorry. 1 minute. Let us take, let u bar is equal to x1, x2, x3, and v bar is equal to y1, y2, y3. U bar plus v bar is equal to x1 plus y1, comma, x2 plus y2, comma, x3 plus y3. That is same as y1 plus x1, y2 plus x2, y3 plus x3, because they are real numbers. X1 plus y1 is equal to y1 plus x1. That is v bar plus u bar. Therefore, v plus is abelian. Closure is satisfied, associative satisfied, identity, inverse, and commutative. The next thing is, take an element in V, that is R cube. Here your V is R cube. Take a real number C. This is a field here, and multiply Cu bar, that is Cx1, Cx2, Cx3. C is a real number. Xi is a real number. So Cxi is again a real number. That means Cx1 is a real number, Cx2 is a real number, Cx3 is a real number. So they belongs to R cube. So scalar multiplication is closed. Scalar multiplication is closed. Next, what is the other properties? You have the four more properties. What is that? U bar is equal to x1, x2, x3. So let us C comma D belongs to R. C plus D into U, that is C plus D into x1, x2, x3. That is C plus D into x1, C plus D into x2, C plus D into x3. That is same as Cx1 plus Dx1, Cx2 plus Dx2, Cx3 plus Dx3. That is same as Cx1, Cx2, Cx3 plus Dx1, Dx2, Dx3. That is same as C into x1, x2, x3 plus D into x1, x2, x3. That is same as Cu plus Du. So C plus D into U is Cu plus Du. What is one more property? C into U plus V. So that is C into U is x1, x2, x3. V is y1, y2, y3. Both belongs to R cube. C into U plus V is C into x1 plus y1, x2 plus y2, x3 plus y3. That is Cx1 plus Cy1, Cx2 plus Cy2, Cx3 plus Cy3. This can be written as Cx1, Cx2, Cx3 plus Cy1, Cy2, Cy3. That written as C into x1, x2, x3 plus C into y1, y2, y3. That can be written as Cu plus Cv. So C into U plus V is equal to Cu plus Cv. Next, one more thing, one more property. C into Du. That is C into D into x1, x2, x3. That is C into dx1, dx2, dx3. That can be written as CD x1, CD x2, CD x3. That can be written as CD into x1, x2, x3. That is CD into U. So C into Du is equal to CD into U. Next, 1 into U. That is 1 into x1, x2, x3. That is x1, comma x2, comma x3. That is nothing but U. So all the 10 properties are satisfied because R cube with respect to addition is a abelian group, scalar multiplication is closed, and all these 4 properties are true. Therefore, R cube of R is a vector space. So any problem, if I ask you to prove it is a vector space, what we have to do? We have to check all these properties. If any property, at least one property is not satisfied, then we can say that it is not a vector space. Similarly, you can show that R power n are also vector space. R power n means you have n tuples, x1, x2, xn. Each one is a real number. So in the same manner, we can show that R power n of R is also vector space. Okay, one more problem. Show that the set of all points of R square of the form 3s, 2 plus 5s is not a vector space. So by showing that it is not closed under scalar multiplication. So what is your H? The set of all points 3s, 2 plus 5s. For example, let us take an element. For example, you take let S is equal to 1. Just if I am taking an example, you will get 3, 2 plus 5, 7. So let us take 3, 7 belongs to H. Let us consider a real number. Let C is equal to some 2, any value. That's your wish. Let us take C that is equal to 3 or 2, whatever it may be, belongs to R. I am asking you to find out, take it as U. Let us take Cu. What is Cu? 9, 7 3s are 21. So my question is, either Cu should belongs to H because scalar multiplication should be closed. So Cu should belongs to H means 9, 21. Is it belongs to H or not? That is our question. So if it is belongs to H, it should be in this form. That means 3s should be 9 and 2 plus 5s should be 21. 3s is equal to 9 means s is equal to 3. 2 plus 5s is equal to 21 means 5s is equal to 21 minus 2. That is s is equal to 19 by 5. So you are getting two different values. One is s is equal to 19 by 5. and one is S is equal to 3. That means the CU does not belongs to H. So the elements in H should be in this form. That is 3s comma 2 plus 5s. So if this 921 should be there in H, means there should be same S value. For that, this element should be there. But I am getting two different values. S is equal to 3 and S is equal to 19 by 5. So this is not possible. So this 921 does not belongs to H. This means scalar multiplication is not closed. Is not closed. Therefore, H is not a vector space. Vector space means the scalar multiplication should be closed. Okay, if one property is not satisfied, then it is not a vector space. So it is H is not a vector space. Take one more example. See, the H value is the set of all elements such that x square plus y square is less than or equal to 1. Let us take a vector u bar, that is 0, 1. Here 0 square plus 1 square, that is 1, less than or equal to 1 means definitely u belongs to H. Let us take one more vector 1, 0. 1 square plus 0 square, that is 1. This is also belongs to H. I have taken two vectors u bar, v bar belongs to H. Now u bar plus v bar, that is 0, 1 plus 1, 0. So what is the answer? You will get 0 plus 1, 1, 1 plus 0, 1. But 1 square plus 1 square, that is 1 plus 1, 2. So here the condition is it should be less than or equal to 1. 2 is greater than 1. So u bar plus v bar does not belongs to H. That means vector addition is not closed. Vector addition is not closed. So if vector addition is not closed, it means it is not an abelian group. So this property is not satisfied. Similarly, you can take a vector. For example, you have taken u is equal to 0, 1 belongs to H. For example, let us take C is equal to 2 belongs to a real number. Cu, that is 2 into 0, 0, 0, 2. 0 square plus 2 square, 4 greater than 1. Cu does not belongs to H. So scalar multiplication is also not closed. Is also not closed. Therefore, so I should produce an example. So if you give an example that vector addition is not closed, it is enough. Or you can give an example that scalar multiplication is not closed. So if any of these properties are not satisfied, then we can say that it is not a vector space. So these are some examples of vector space. So tomorrow I will explain you about properties of vector spaces. Okay.